Okay. We are section 1.5, and today we're going to be going through the proofs, much like you did in the outlines. But I'm actually not going to take the time to do all the proofs. We don't have that much time, as you guys are well aware. So, there are, first I put the different forms, proof by contraposition of P implies Q. The contrapositive would be not Q implies not P. And so you assume not Q, you show therefore not P, conclude not Q implies not P, and therefore P implies Q. So that's going to be your contraposition. Proof by contradiction. Contradiction is you're going to assume not the phrase. Notice this isn't P implies Q. This is not the entire statement. So you're assuming the entire statement is incorrect. And you're going to show that therefore Q, which is not necessarily part of the original theorem statement, and not Q are going to be true. So you're going to have two statements that you're going to show are true, but they're contradictory to each other. And from that, you conclude that P has to be true, because if P is false, then you arrive at contradictory statements. So that's proof by contradiction. And then a two-part proof of P if and only if Q. You show P implies Q, show Q implies P, and therefore P if and only if Q. The biconditional, you're just going to start with P and get to Q using if and only if statements all the way down. You don't have to do it two directions. So those are the four types of proofs that we're looking at. We're going to start with a proof by contraposition. Which of these first two do you want to do in class? Proof by contraposition. In other words, which one did you understand least of the examples in the book?
Those two weren't so bad.
Yeah, neither of them were that bad.
I don't know.
Take a vote. Who wants to see the first one? Who wants to see the second one? Everybody has to vote. Who wants to see the first one? Okay. And yeah, that makes it over half that way. We'll do the first one. Well, I assume then that meant yeah, if you don't vote for the first one, you're voting for the second. So, what is the hypothesis for this? Yeah, let m be an even let m be an integer. Assume m squared is even. So we have to get both of them. Now, we're actually proving by contraposition. So what does that mean that we are actually trying to do? Maybe that's what I should put up here.
We're gonna assume that m squared is not even.
Yeah, that's exactly right. We have to fix that. So the contrapositive of the statement is let m be an integer. True that if m is not even, then m squared is not even. So the hypothesis would be m squared is m is not even. I'll go with that and then get to the odd. Well, if m is not even, and remember we're trying to get down to show that m squared is not even. That's where we're trying to get to. What does it mean to not be even?
It means
Yeah, that means it's odd. So that says that m squared, m to the w sometimes. And if m is not even, then m is odd. You see how we're kind of working from both ends to the middle? That's what we're going to do on all these. So then m is odd. Well, what does it mean for m to be odd? Well, I'm not going to jump straight to that. We're actually going to prove that. But yeah. Mm-hmm. Oh. So there exists an n in the integers. And that means that I have to be down here too. There exists a k in the integers such that m squared is equal to 2k plus 1. That's where we're headed. That makes sense? And we have to close the gap here. How do we get from m equals 2m plus 1 to m squared equals 2k plus 1? Yeah. By squaring, we're going to have m squared is equal to 2n plus 1 squared, and that would be what?
Plus 4n.
4.
1.
Yeah, shouldn't that be a 4n squared at the beginning? Yeah. So we're trying to get to a 2k plus 1. Yeah, so factor the 2 out. I'm going to line these up because it's going to start overrunning on the end. As you noticed on some of your outlines, I put overrun where it was going over the boundary. And what you're going to want to do is keep this so that it stays in the middle, a third to a quarter of the middle of the page. Because when this starts getting big, it changes the font size on that. And so it'll actually go over the edge if you're not careful. So factor out the 2, and we get a 2n squared plus a 2n plus 1. And now we're just going to call that a 2k plus 1, where k is equal to 2n squared plus 2n is in the integers. So now I know that thus m squared equals to 2k plus 1 is odd. And what does that tell us then? So I know, well, I kind of have that stated right here. M squared is odd. So if m squared is odd, we started with m is odd.
M is odd, then n squared is odd.
Counterpositive. If m squared is even, oh yeah, therefore, so I see which conclusion. And so if m is odd, then m squared is odd. By contraposition, okay. Any questions on that? Now, I can get rid of my scratch work from the bottom. We are going to skip the proof by contraposition. We're going to go to a proof by contradiction. Prove that the graphs, okay, we have 4 of them to choose from. I'm going to do these two down here, square root of 2 and the set of prime numbers. Those 2 we have to do, and we can do one or the other of those up there if we want. But let's do square root of 2 as a rational number. I've been teaching something more than 14 years. And I have always put one of these 2 as a proof question on a test. So it would be to your advantage to learn these two proofs, square root of 2 is a rational number, the set of prime numbers is infinite. Those are two famous proofs. The absolute proof? Which one are we talking about? The absolute value one? There usually is an absolute value proof on the test. But I have more than one to choose from. The prime numbers one and the irrational. Those two.
I wasn't getting the prime numbers one, I'll be honest.
Okay, we're gonna do them both. We'll start with the irrational two because that one's first, and then we'll do the other one. Now, you guys read the little history behind the square root of 2 being irrational, and they actually threw someone overboard and let him drown because of it. They were very particular about their numbers. It was almost a religion to them, very close to a religion to them, about their numbers. And so when they're coming up and saying that you can't write everything as a fraction, that distressed them greatly. So let's look at how he proved this. We're doing proof by contradiction. So what is the negation of this whole statement?
2, we're at the 2 is irrational.
Yeah. No, I wanted to do that. There we go. Delete. The square root of 2 is irrational. It is rational. We're going to assume the negation. A proof by contradiction is assume not P. So this is not P. So what's the hypothesis?
Assume that
Yeah, assume that the square root of 2 is rational. Now, apply your definition of rational.
one number over another.
Yeah, it's a fraction. There exist two integers, a and b, with b not equal to 0. We can't divide by 0. And the greatest common divisor of a and b is 1. They have no common factors. I got off.
That's given.
Me too, and I always forget. There's some insert is supposed to turn it on and off too, if insert's easy to find. Okay, so they share no common factors. Such that the square root of 2 is equal to a over b. Now, we are trying to arrive at some contradiction, but we have no idea what that contradiction is going to be. So at this point, we are simply left massaging this equation. If you want to simplify that equation, what would you do to it? Square both
Did you
sides.
say massaging?
Yeah. Sorry, that's an old term. That's actually more of a physics term than anything because physicists don't like to show all their steps. They show their initial and the conclusion, and everything else is left to you to figure out. Mathematicians are pretty good at that too. The squaring both sides gives 2 equals to what? And then what do we do? We're still trying to simplify. Yeah, multiply. Get rid of the b squared. So multiply both sides by b squared to get, and then we're going to have 2b squared is equal to a squared. What does that tell you about a squared?
It divides into b.
Yeah, that's one thing we could say, but that actually doesn't help me much because I don't know it goes into b squared.
It's even?
It's even. Yeah. Yeah. Since a squared is a multiple of 2, a squared is even. Now, we have Euclid's lemma, and I thought I put it up here. Let's go up and see if I typed it. No, I didn't. What does Euclid's lemma say? You've been sort of using it. If a prime number divides into the product of two numbers, then it has to divide into one of those two numbers. Okay? If a prime number divides into the product of two numbers, it has to divide into at least one of those two numbers. Notice that doesn't work if you're not starting with a prime number. If you're saying, a multiple of two numbers, say 10, divides into something. You don't know that 10 has to divide into both of the products that you're going for. It might only divide into, just one of its divisors divides into them. So you have to start with a prime number. If you're starting with a prime number, you know it has to divide into the product. I know that 2 divides into A. What does that tell you about A then?
Even.
A is even. Hey, I suppose we could have used a proof of the one we just did at the beginning too.
We already,
We
Oh.
already showed that, yeah. Mhm. But you actually need the idea of Euclid's lemma because I think you have to use multiple of 5 on any homoplane. Or a multiple of 3. So A is even. What does that tell you if you apply the definition of even? I know A has to be 2 times some integer, right? Now we're almost done because we know something about A squared and B squared. So we can substitute in for A squared, and we'll get to our conclusion. But what is 2k squared equal to? 4k squared. I wrote 2, didn't I? Really don't want to multiply those 2's today. That's the second time I've done that. What that tells you, so that we can simplify, we're going to have 2b squared is equal to 4k squared. What do you think we should do now? Divide by 2. So you're going to have b squared is equal to 2a squared. Apply your definition for b squared. Therefore, b squared is what? And hence, yeah, b is even, which gives us our contradiction. Both A and B are divisible by 2, which is a contradiction because we assumed that they had no common factors. I'm off on again. I was off on just that one last time. Therefore, go back and fix what we broke. Square root of 2 is irrational. Question?
when we're saying, we have the assumption that they have no common factors, it's like we're looking for the most simplified fraction form. But, so when we solve it out, we see that there exists a form that is not these common factors. What does that mean? Like, what does that even mean? Anything?
No, it doesn't mean anything in terms of the proof itself, other than you know that they're divisible by 2, and we assumed that they were not divisible by 2.
Right.
Because if they were, we would have canceled it at the beginning. So we have, they share a common factor, and they do not share a common factor. Two opposing facts that we arrive at inside our proof. Mhm. And you could be proving along and come to the fact that your cat is purple and then your cat is orange. And as soon as you get two opposing facts, which may have nothing to do really with what you're proving, but you eventually get down to these two facts that cannot coexist, then you know you're done. Your assumption was wrong. So you have to go fix your assumption. And that's the way proof by contradiction works. It's a very powerful proof method, but it's somewhat annoying because you're not sure what those two facts are that are going to be contradictory. You have no idea which direction to go as far as that goes. You just start playing with your proof until you arrive at something that breaks. Yeah. It is fun. I think you have to do square root of 3 or square root of 5 or something like that on your homework. So you can mimic it. Show that the set of prime numbers is infinite. This is a very famous proof too. This is proof by contradiction, so let's go ahead and make the negation of this because we need to know what not P is. So what would be the negation of the set of prime numbers is infinite? Yeah. I'm going to skip prime numbers. It's finite. So that's what we have to assume. That's our assumption here. Well, we just go from what we know. If we know that this set of prime numbers is finite, then we had sure better be able to list them all. Okay. Well, in theory, we're just going to name them. And so all these prime numbers are going to have P1, P2. Do they use N? They use K. Yeah, because we're going to use N for something else. So that's my list of prime numbers. And I'm going to say these K prime numbers so that's how many of them I have. Well, someone gets the cute idea to think about prime numbers are used to make all the other numbers by multiplying them together. So we write the product. And we're going to call it N. And we're going to add 1 to it. So N is going to be 1 larger. I'm just going to say consider. Take all of our prime numbers, multiply them together, add 1 to it. That's bigger than any of these prime numbers right here, correct? That's not what I want. It's bigger than all of those. It can't be in that list. Question?
Okay, but I guess I was confused. Maybe I was not understanding what they were saying. When they introduced that step and they said that we made up a number N that will not have any of the E of I, whatever it is, as prime factors. Then it goes on to say that N is a natural number, so it has a prime divisor as Q.
Yeah, so I'm getting ready to show you why. They skipped a whole paragraph in that sentence.
Okay,
Right?
they lost on that though.
Yeah, they did. N is not in the list of prime numbers. So is N a prime number?
No.
No. Well, if N is not prime, then it has to be divisible by at least one of those prime numbers.
Right.
We're gonna just say Q. And I'll put it in so you see. So Q is in that set. It's one of them. I don't know which one it is. So rather than trying to mess with the notation of it, I'm just going to call it a Q. Because that's all the prime numbers we have, and n has to be divisible by a prime number because it's not in the list of prime numbers.
So why do they say that they have a number n which will not have any of those prime numbers as a factor?
Yeah, don't worry about that part because we're going to actually show that. Yeah, that sentence is confusing. Just strike it out. It's not necessary to the proof.
Okay.
You're just making this n it's bigger than any of the prime numbers, so it's not in the list, which means it's not prime, which means it's divisible by something in the list. That's all I need. I also note that Q divides the product. I need this space right here. P1, P2, PK. Q has to divide that product, right? Because Q is one of them. Okay, so if Q is one of them and you multiply them all together, then maybe Q is this P2 right here. So if you multiply it all together, you should be able to factor that Q out. That's all they're saying. So I know that Q divides that product. And so there exists, I don't know, an R in the integers such that Q times R equal to the product P1, P2, PK. Q times something equals that product. Now, what we're going to do is look at this n minus this product. If I subtract that product from the n, I'm going to get left with 1, right? I have 1 is equal to n minus P1, P2, PK. But that's n minus Q times R. But I know n was divisible by Q. I'm going to put right here n is equal to Q times W. Some W in the integers. So now I can come down here and I can put this as a QW. Now what do you think we should do? Factor out a Q and we get W minus R. Well, W minus R, and this equals Q times, I don't know, S. Where S is equal to W minus R as an integer. What is that telling you? Let me put it together for us. We used F already. Thus, QS is equal to 1.
Both have to be 1.
They both have to be 1 or they both have to be minus 1. And I really don't care about the S. I just care about the Q. Yeah, and hence Q is not prime. So what were the two contradictory facts that we have come up with? Yeah, up here we knew that Q was prime. It was one of those prime numbers. Down here we showed that Q is not prime, so we have Q is prime and Q is not prime. They can't both happen. So let's fix our hypothesis. Thus, the set of prime numbers is infinite. Very important proof. Yeah, I filled in a few more of the details than the book does on this one. And they make that confusing statement.
Yeah, that was, because like I was reading most of what they were saying, it seemed to make sense. It was just weird. They were like, it has no prime factors, now it's divided by a prime number. So I was like, I don't know if that's.
Yeah, that it was just misleading.
Yeah.
Yeah, we'll cross out that sentence and we're good. Okay, we're skipping the diagonal proof. This, to be a magic square, you just have to have the columns and rows and the diagonals. Sum has to all be the same. And so they did a proof with that. Let's look at a two-part proof and a biconditional part proof. We need to do both of those. The two-part proof, let m and n be integers. Then m and n have the same parity if and only if m squared plus n squared is even. So what is the big hypothesis? What is a big statement before it gets to our little substatement? Let m and n be integers. Okay. Now, we have to do this going two directions. It says m and n have the same parity if and only if m squared plus n squared is even. So what I like to do here is I like to put the direction that I'm headed so that I know where I'm heading. And right after that then, our assumption for that would be that m and n have the same parity. Well, what did it mean to have the same parity? They're both even or both odd. So now that means we have to do cases. So case one. M and n are both even. Oh, what does it mean for m and n to be even? Yeah. Yeah, b-ply, let's fix that. By. By applying, yeah, that's a shortcut of that word, yeah. There exist integers. What do we want to call them? I need two integers. K and I. No, we'll get that next time. There exist two integers, K and I, such that we're going to have m is equal to 2k, and I missed the m, and n is equal to 2i. Now, where are we headed?
M squared plus n squared.
Yeah, we want m squared plus n squared is even. What does it mean for m squared plus n squared to be even?
2 times some integer.
Yeah, so what we actually need then is that m squared plus n squared is equal to a 2j, okay, is equal to some 2j. Well, how are we going to get to m squared plus n squared equals to 2j when I have an m is 2k and an n is 2i? Squaring and adding, right? M is 2k, so we have a 2k squared plus a 2i squared. But what is 2k squared when we square it?
4k squared.
4k squared. And how about for the 2i? 4i squared. Now we need it to be 2 times something, so factor out a 2. And now we call that a 2R. No, 2J. I was going to call it an R. J was suggested.
It's great to put that
That where?
in,
Oh, in the integers?
yeah, so you want us to put that right over.
Yeah. I want to see that. I need to know that you recognize that as being an integer.
Yeah, I usually just type it out in Word.
That's fine. You can do it either way you want. Okay, so that's the first case. What's the second case?
Cool.
Then what should we do?
Find them as a-
Yeah, by definition of odd, there exists integers. What do you want them?
the lambda.
And so we're going to have m is equal to 2 lambda plus 1. Oh, that did not work. Got an F instead of a G.
That's crazy.
Lambda plus 1.
I know.
Notice up here, if there exists, I don't need integers because I have element and integers. Okay, so then what did we do next?
We can either work to the end or squaring that.
Yeah, by squaring and adding or substitution, however you want to say it. Algebra. So that's going to be 2 lambda plus 1 squared plus 2 sigma plus 1 squared. Now, where's that? 4. I missed my 4. Lambda squared plus 4 lambda plus 1 plus 2 sigma squared plus, oh wait, 4 sigma squared. We can square it when there's lambdas, can't square it when there's sigmas. I don't know why. It just, yeah, it seemed like a 2 was appropriate there. Okay, and then what? Add the ones together, right? Oh, well, let me add the ones and then factor the 2 out. Yeah, you're ahead of me. That's a good thing though, that you can see that step. That's a very good thing. And then factor the 2 out. So then you're going to have 2 lambda squared plus 2 lambda plus 2 sigma squared. And what's that equal to? 2 times what? Some integer. Give it a name. T. Where T is going to be all of that because I'm tired of typing it. I'm going to copy it and paste it.
I literally just copy paste and
Yeah, that's one way to do it too. And I can tell when you do it because sometimes you forget to, you'll start off with the right variables and then you forget to change them halfway through. I see that. I know exactly what happened then. Where T is equal to as in the integer. So what is our conclusion? Now we have our conclusion here. Thus, if M and N are the same parity, so that's the first direction. So now let's go back the other direction. Nope, wrong arrow. There we go. Yeah, this one is 4 parts. We're just going backwards now. So that means that we need our cases. What's our first case? Actually, one of them, yeah. Because what we have to do is show that if m is even, then n is even. And if m is odd, then n is odd. So m is even. If m is even, what do you think we should do? Should be, yeah, well, let's square it in a second. Define it even first and then square it. What'd you call it? E? Oh, well, there exists an E in the integers such that, we got the E on the thingy, such that m is equal to 2e. Now, what do you think we should do with this m? Square it. And we know that m squared plus n squared is even, so let's write down what that means. Oh, we'll go with a G. And we're going to need that. We're going to have m squared is equal to 4e squared. And by substitution, we're going to have n squared, which is equal to right? I add and subtract n squared. Oh, I have to add and subtract m squared. Yeah, we want an n squared here. This should be an m squared, and this should be an m squared. Yeah. Add and subtract our m squareds. But what is n squared plus m squared?
It's an even number.
Yeah, it's our 2g that we have from up there. So we're going to have our 2g minus, what is our m squared?
2e squared.
Yeah, 4e squared. Factor out our 2. It's going to be g squared minus 2e squared, which is equal to, because it was e squared and everything's squared, right? That's equal to 2w, where w is equal to g minus 2e squared is in the integers. So what do we know then?
N squared is even.
Yeah.
Or n is even.
By the first proof we did, we believe that n is even. Now, the second case, what is this one going to be?
That n is odd.
Can we copy and paste? Do you think we can make it through all of that? And change it appropriately? Sure, we'll try it. Yeah, I know. Best thing. I'm tired of typing. So if m is odd, there exists an e in the integers, so that would be 2e plus 1, right? Well, we can reuse our variables. We don't have to name them new things. But square it, then what do you get?
4e squared plus 4e plus 1.
And by substitution, n squared equals n squared plus m squared minus m squared. So that's 2g minus, right? And then we want to factor out our 2 from those first things. So it's g minus 2e squared
Minus 2e.
minus 2e. And what should we do with this?
Minus 1. Do that again.
Yeah, but we'd really like it to be a +1, right?
Sure.
So what we're going to do is we're gonna add 2 and subtract.
You already subtracted 2. Yeah.
Yeah, and these two will make a +1 for me, and this will make a -2, which when I factor it out becomes a -1.
Yep.
Right?
Sure.
Sure.
Yeah. Let's put it in between steps so we can see that. You guys are agreeing with me too well. I know. Yeah.
I didn't do it because, I don't know, just because I thought, if you have a -1, it's like the same as having a +1. In terms of being.
In terms of, yeah, by the strict definition,
Yeah.
yeah. So then that becomes 2W plus 1, and this is going to be our W.
You guys can think I'm We all know where that's from.
And so n squared is what?
Odd.
Now, we can't exactly go to the first part of the proof, or did we have one? I forget. Seems like we might have had one up here. Yeah, that was our proof by contradiction. It's up here, we'll get to it. If m is not even, then m squared is not even. We have if m squared is not even, then m is not even. So we can't exactly use that. So now we actually have to do the work.
I thought we had if m squared was not even, then m was not even.
That wasn't at the beginning, we had the converse of that.
Uh,
And converses aren't always correct. So n squared is odd. We have to show that n is odd.
Just copy paste what you just did.
Just have 2w plus 1 squared, or square root, wait.
Yeah, because copy.
How about proof by contradiction? Just a little baby one in between here.
Yeah.
Yeah, okay? So if n is even, then
Oh,
n squared is even by the by one of our first. It's not the first proof. It's one of our homework problems that we did last class period.
sure.
Yeah. By
By the homework.
a homework problem. That's good enough. And so, if n is even, then n squared is not odd. Right? So what would that tell us? If we assume that n was even here, then I know that n squared can't be odd. But we know that n squared is odd, therefore n has to be, yeah. So if n is even, then n squared is not odd, which contradicts the fact that n is odd.
Which means that it's equal.
Yeah.
Odd. It's so
It is confusing. And so what have we proved?
The
M squared plus N squared.
n squared plus n squared is even, then that's n squared.
Yeah. Yep. And it's in parity. All I did was I came up here and I hit enter. You can see it has an enter right there. And it put a proof symbol down here when I did it, and I just hit backspace to remove the proof. Okay. You guys have looked at this comparison of the three of them. Oh, I put Euclid's lemma right there. Now you have it. Let's look at this biconditional one, which is actually a really short proof, and then we'll be done. the proof uses a figure in the book, so we're going to just reference the figure in the book. And what we're going to do is we're going to let a squared plus b squared equals to c squared. Yeah, and plug this into the law of cosines. So what we're going to have is a squared plus b squared equals to c squared. And that was, I forgot my law of cosines. Let me look at it.
2AB plus cosine theta.
Yeah,
Oh, or is it
minus
tan theta?
2ab cosine theta, the angle between. Couldn't remember whether it's minus or plus. Okay, so what we're going to do is we're going to plug that in. What that means is that this a squared plus b squared is all equal to c squared, and so I can cancel both sides, right? I'm doing an if and only if arrow because I can cancel. That cancellation is not something that's going to give me problems. I can go both directions. I can start at the top and go down, or I can start down here and say 0 is equal to 2ab cosine theta, and go up here by adding the a squared plus b squared to both sides. I can do it either way. You guys see that? That's what this if and only if arrow says. You can go either direction. You start up here and get down here. You can start down here and get to up there. But we're assuming that a, b, and c are non-zero integers. So what does that tell you right here?
That 2AB cannot be 0.
Yeah. So that tells you cosine theta has to be equal to 0. Well, what's the only angle cosine is equal to 0 at?
90 degrees.
90 degrees. And so a squared plus b squared equals to c squared if and only if. Yeah, what? Well, we're looking for something between 0 and 180 because we're talking about the angles of a triangle. Yeah. So if and only if the triangle is a right triangle. So up here we should assume, we should say, assume, well, we're going to let this be, I'm going to reword this. I don't like how I've got it started, and then we'll be done. Yeah. Assume that the triangle is a right. Actually, we can word it this way. If the triangle is a right triangle, then, and it'll be pretty. If the triangle is a right triangle, then a squared plus b squared equals to c squared. A, b, and c are non-zero integers, and plug this into the law of cosines to get, and then you can do your if and only if on it. There we go. And you guys can look over that last proof down there. We're done. Remember, next time we're working on homework in class. If you have any questions on any of the outlines that you turned in today, you can also bring those to class next time. That's fine.
7A. This is for the assignment that's due tonight. I may have worded it weird, but
No, she doesn't think
I
so.
got it.
Okay, let me stop this broadcast right here.